For chapter 14, we're going to get into the equilibrium of acids and bases and really dive into what it means to be a strong or weak acid or base and how that affects pH and equilibrium. An important point here going forward is that hydrogen ions, when they're aqueous and in water, often attach to water to make this hydronium, and they are equal. It's a pretty simple equilibrium or reaction, but chemically they behave the exact same way, so it doesn't matter if we have one or the other. In a balanced equation, they're interchangeable. We can say the hydrogen is equal to the hydronium. It doesn't matter if the hydrogen is on the water, next to the water, off the water, touching the water. Those hydrogen ions are able to react with anything they come in contact with. So hydrogen is the same as hydronium. Okay, so here is a formic acid, HCOOH, and we need to write ionization reactions, which is just a balanced equation, conjugate acid-base pairs we'll talk about, and the equilibrium expression. So first we need to recognize that formic acid is an acid. There's two ways we can do this. Typically when we have an acid, we can just say HCOOH dissociates into an H plus. And then with this one, when we have that HCOOH, that's actually a group we call a carboxylic acid. You might remember from biology. This hydrogen on the end is actually the acidic one. The one attached to the oxygen is held on weaker. The one onto the carbon is a little bit of a stronger bond. The one that comes off is that hydrogen. So we say H plus HCOO minus. Now that's just a simple dissociation. But when we talk about the word ionization, we mean that HCOOH can actually react with water. And this is where the hydronium comes from. It forms an equilibrium with it makes H3O plus, and then the HCOO minus. Chemically, these equations are the same thing, but that second question that says identify the conjugate pairs, we need to do this. So the K expression for this is pretty standard. This is liquid water because it's in liquid. Everything else is aqueous, and we say Ka's because they're acid. Hydronium, H3O, times HCOO minus over HCOOH. And if we did the equilibrium expression for the top reaction that just dissociates, it's the same exact reaction because we don't put in the liquid water, so that doesn't matter, and hydrogen and hydronium are equal. So the K expression is going to be the same for both. But in order to get a conjugate pair, we label this and we say, okay, this is an acid. Acids donate hydrogens. And we said that bases accept hydrogens. When that hydrogen comes off, what it does is it turns into HCOO minus. That HCOO minus, that negative charge, now allows it to take a hydrogen back when it goes with the reverse reaction. So this is actually a base. We call it a conjugate base because that's what the acid turned into. Now, if we look at the water, this water actually accepted a hydrogen. To turn H2O into H3O, it accepted a hydrogen. That is the definition of a base. So this one at water is acting like a base, totally fine. Which means that H2O is turning into H3O, and H3O is my conjugate acid. So we need to find the pairs. We can't do that with this top reaction if we leave the water out, because we need the water. The water is acting like a base and turns into hydronium. So I have an acid base here, and then I have a conjugate acid base here with the formic acid. And we can go through the same thing with the perchloric acid, HClO4. Plus H2O makes hydronium plus ClO4 minus. The Ka expression for this one is going to be H3O, same thing. Products over reactants, ClO4. All the coefficients for acid-base problems are conveniently 1, and the water will never be included because it is a liquid. Okay. So then identifying the acid-base pairs, here we have my perchloric acid, and it turns into a base, conjugate base. So the ClO4 is able to accept ions. That negative charge, hydrogens are positive, so negative ions are typically, not always, typically able to act like bases. That if my perchloric acid is the acid, that means my water is acting like a base. It's accepting the hydrogen, which turns hydronium then into a conjugate acid. And that's my acid particle. Hydronium is the same as hydrogen. That's what an acid is. So it's a conjugate acid. And here we get into the word strength. Strength has to do with equilibrium. So if we put our generic equation up here, HA, generic acid, turns into H plus and A minus. Here's where the equilibrium comes in. If I say something is strong, strong means it favors the products. K is going to be bigger than 1. If I say it's weak, weak means it favors the reactants. K is going to be less than 1. And when it favors the products, strong acids are so strong that we actually don't think they're equilibrium problems at all. We call them limiting reactant stoichiometry problems because it's virtually 100% of them that react. It almost leaves nothing unreacted. Weak ones, however, favor the reactants, and very, very few of them actually break apart and dissociate. They're represented by molecules. So here we've got a strong and weak equilibrium. Do I favor the products or the reactants? And that's different than molarity. Molarity is just how many do I have. Strength and molarity are not the same thing. So let's draw the following 4 scenarios. A. If I had a dilute strong acid, well, dilute means a few, and strong means dissociated. So I have H plus and A minus. So H plus, A minus, I'll draw one more. Okay, strong, dilute. If we did B, dilute and weak. Well, dilute means a few, and weak means it favors the reactants, HA. So I'll draw a couple of these. These are not dissociated. The molecules are connected. The H is not coming off. I just have a very few of them that are weak. Concentrated means a lot, and strong means it favors the products. So they're broken apart. So I've got a bunch of these. And 100% strong means they're all going to be broken apart. There's water in the background of these too, but we don't typically draw the solvent. Concentrated again means a lot, and weak means it favors the reactants, HA. So if I were to draw this one and visualize what the particles look like, they're all HA molecules. None of them are broken apart. There are no charges on them. This is the funniest one. Ha ha ha, ha ha ha. It's funny, you laughed. Okay. So concentrated versus strong, they mean two different things. It's how many do you have, and then are they dissociated or not? Do they favor the products or reactants? So there's a chart in your book to look up Ka expressions or Ka values for various acids. So you're going to be referencing that a lot. This one says, use your book knowing Kw for water. Water is kind of a special one here. 1.0 times 10 to the negative 14th. That's not really in an acid chart because it's water. Water can do multiple things. Arrange them in order of strength. So we need to look at their K values, and we can compare them directly because they're all 1-to-1 ratios, and we can see which ones are the strongest, which ones are the weakest, etc. So the first thing we need to do is look up their K values. So let's get those out of the way. First one, HOC6H5. 1.6 times 10 to the negative 10th. Water, we already said, 1.0 times 10 to the negative 14th. HSO4 minus, 1.2 times 10 to the negative 2nd. NH4 is 5.6 times 10 to the negative 10th. And NO3 minus is just a strong acid. You won't find that in the chart. Strong acids don't have equilibriums. They go 100% break apart. So we arrange them in order strongest acid to weakest acid. Well, the strongest acid is going to be HNO3 because it's a strong acid. That will be bigger than HSO4 minus. It's 1.0 times 10 to the negative 2nd. And if you just take their values and you put them in order, NH4 is going to be in the middle there, which is a little stronger than HOC6H5. And then it makes sense, we would hope, that water is the weakest acid of the group. Water is very weak, 10 to the negative 14th power. So this is my strong acid, and this is my weakest acids by their K expressions. Now this next question says, arrange their conjugate bases. So we have to know what their conjugates are. If we take off a hydrogen, we have the conjugate. So my bases for HNO3, my conjugate base is just nitrate. Take off another hydrogen and we get sulfate minus 2. Take off a hydrogen on NH4, we get NH3, that's a base. Take off a hydrogen, the one on the oxygen, OC6H5, and then H2O, take off a hydrogen and we're left with hydroxide. So getting the conjugates is just a matter of removing the hydrogen. Then put them in order of strength. Well, they're going to be opposite in strength. So if my nitric acid is the strongest acid, the nitrate will be the weakest base. And then conversely, this one makes a lot more sense. If water is my weakest acid, the conjugate of water is going to be hydroxide. That will be my strongest base. So these are in reverse order of their molarity, of their acid strengths. The conjugates are stronger or weaker relative to what their values are for Kas. And we will actually, at another point here, mathematically talk about Kb's and how to calculate these values. And we can justify it, but for now, we just want to know that they're opposites and how to identify and find the conjugates. All right, calculate the hydrogen or hydroxide necessary under each of the following conditions. Kw, our equation is H plus and OH minus. Hydrogen times hydroxide is Kw, and Kw we know is 1 times 10 to the negative 14th power. We will use that a lot. So calculate the hydrogen. If the hydroxide is 9.3 times 10 to the negative 4th, the hydrogen here is going to be 1.08 times 10 to the negative 11th molarity. Calculate hydrogen and hydroxide for a neutral solution. A neutral solution is going to be, if we have our expression, let's make some room down here at the bottom. H2O liquid makes H plus and OH minus. It's a 1-to-1 ratio. If we looked at like a full ice chart for this, it does not matter how much water we have because the liquid doesn't go in the expression. So we just realized that my H and my OH are just X values. So my K expression is X squared. So the square root of KW will give me this answer here. Kw is going to be X times X, hydrogen and hydroxide. So this is where the hydrogen will be equal to the hydroxide, which is really what neutral means. pH is 7, but it really means hydrogen and hydroxide are equal. 1.0 times 10 to the negative 7th. All right. Then the last one we can just plug in as well. Calculate the hydroxide if the hydrogen is 6.7 times 10 to the negative 11th. So the hydroxide then, we plug that into the Kw expression. We get 1.49 times 10 to the negative 4th. So here's where we need to have these rules. This is where we're defining pH. pH is going to be the negative log of the hydrogen or hydronium. We're going to get another term here. If we can measure the concentration of hydrogen, I can do the same for the hydroxide. We call it a POH. pH is the one that tells me my acid-base scale. It is a pH scale, not a POH scale. pH, so look at that number. Kw we've already looked at, but if 10 to the negative 14th is hydrogen times hydroxide, and we take the logarithm of all of those, 14, my exponent's there, the negative logarithm, 14 equals pH plus POH. So that gives me a way to go between those just by looking at the pHs, because the pH is an exponential scale. And we get a new sig fig rule that says the concentration, sig figs, are going to be equal to the number of decimal places in the logarithm. Not holding you high and tight to that, but we're pretty close there. I'll show you what that looks like. Some mental math here, just so you know how logarithms work. These clean numbers, 1.0 times 10 to the something. What is the pH if the hydrogen is 1.0 times 10 to the negative third? Negative logarithm of that, pH is going to be 3. And technically here, if there are 3 sig figs in that concentration, I want 3 decimal places in my logarithm, 3.000. And what is the pH? What is the hydrogen if the pH is 4? Well, if it's a clean 4, 4.00, that gives me a very clean concentration. The hydrogen is 1.00, or I'm sorry, 2 sig figs will give me 2 decimal places. 1.0 times 10 to the negative 4th. So that 4 becomes my exponent. This exponent, negative 3, becomes a pH of 3. And here we have a chart that kind of just, you need to be able to calculate all of these numbers very, very simply and quickly using those expressions. So hydrogen and hydroxide, I can go back and forth. Kw equals hydrogen times hydroxide. pH and POH need to equal 14. Or we can do the negative log of the hydrogen equals the pH. And the opposite of that, if you were to solve that equation, 10 to the negative pH, let me just show you that one here off to the bottom. If the pH equals a negative log of the hydrogen, and you wanted to solve for the hydrogen, if you had the pH, you move the negative sign over, and you get a logarithm, log of the hydrogen. And to get rid of that log, there's a button on your calculator attached to the log. We say 10 to the negative pH. It's just the hydrogen. So you don't get this equation, but you're expected to know how to solve for it, how to rearrange this logarithm and to get to this one. So we can use that as well, and that holds for the hydroxide as well. 10 to the negative POH gives me the hydroxide. The H's have to go together if you're talking about hydrogens. The OH's have to go together if you're talking about the hydroxides. Okay, so let's just look at this one. Here we've got a pH 6.88. That is going to very easily give me my POH 7.12. Okay. Negative log of 6.88 is 1.31 times 10 to the negative 7th. And I can either use the K expression or the POH expression here to get the hydroxide. 7.59 times 10 to the negative 8th. Okay. Acid, base, or neutral? Well, that comes from the pH. This one right here. So the pH there is less than 7. This is an acid. Now here we have the hydroxide only. So I can find my hydrogen with the K expression, 0.119. And then negative log of both of those numbers will give me the pH and the pOH, 0.924 and 13.08. pH is less than 7. This one again is going to be an acid. Next one, pH is 10.89, and we can see that that's above 7, so let's just go over here and call that a base. 10 to the negative pH will give me the hydrogen. 10 to the negative pOH will give me the hydroxide. 1.29 times 10 to the negative 11th. And 7.76 times 10 to the negative 4th. This last one here, we don't need a calculator per se. It's a nice clean number. You can do the mental math. The pH of that is going to be 7. And if you're catching on, the pOH is 7. The hydroxide is 1.0 times 10 to the negative 7th. This is a neutral solution. The last problem here looks at the thermodynamics of just the dissociation of water for Kw. Here we've got our balanced equation. H2O turns into equilibrium H plus OH minus. We say this auto-ionizes itself or dissociates the water, or whatever you want to think about it. Here we notice we think about things in very pure conditions. Only at 25 degrees is water 10 to the negative 14th power. And it's only at 25 degrees that a pH of 7 equals neutral. So this gives us a new definition of neutral. Neutral, remember, means hydrogen is equal to the hydroxide. Neutral does not necessarily mean 7. It only means 7 at 25 degrees. It's the square root of Kw. Will give you a neutral pH at any different temperature. And it changes with temperature. So here we have a very simple question. As the temperature increases, K gets bigger. Is this reaction endothermic or exothermic? As heat increases, K gets bigger. K getting bigger means I have more products, more hydrogen and more hydroxide. So that means that in order for an increase in temperature to drive the reaction right, this is an endothermic reaction. Heat going in makes this dissociate more. Chemically, that makes sense too. If you add more heat, you're more likely to separate the hydrogen from the hydroxide and break that bond. Since this reaction only looks at one thing breaking apart from another, that makes sense that it's endothermic as well. But the other important point is pH of 7 is only at 25 degrees. Neutral really means hydrogen and hydroxide are equal.